I'm James Smart with ECD and Broadcom. We're the older Mulx company before being acquired, and we basically do fiber channel adapters supporting SCSI, NVMe, and whatever other fiber channel protocols online. And what I wanted to talk about today was some of the experiences we went through in our LPFC driver patches for the 12.2.00 patch set, which we recently pushed upstream. And most of these patches were strictly for performance, and it was driven by a new ASIC we released that raised the performance levels up about 2 to 3 times what our previous ASICs had been. And we knew by some of the benchmarking that we had already done that we were already hitting some of the limits in the software. So we expected that we had to go through and do some changes to the driver to get it to keep up to the hardware. So what this presentation will walk through is some of the things that we did to actually categorize where we're at, find out where the stack is, some of the major change areas that we made within LPFC, and then I'll also show you what our final results are and some of the OS surprises that we hit along the way. So since we're in a performance slide set, I can't get away from describing a little bit of our adapter, driver to adapter interface. Our term is service level interface. That's what the SLI stands for. We have 2 generations that the LPFC driver supports. One is extremely old and is done in hardware that has very little scalability, and it's really kind of a monolithic sequential engine in it, but it's still found on adapters that ship today in quite a bit of volume, our 8 gig adapters and older. But we did design a new interface which was tailored towards the higher CPU counts that we knew most of the systems were moving to. And we've since released 3 generations of ASIC on that interface. And it's a model where we have quite a few parallel processing engines and a dynamic model that moves the I/O load within the chip to whatever PCI function is actually driving it at that point, while still enabling the data coherency boundaries that we need between ports. The resource levels on it are in thousands of queues, so the notion is that we can have command queues and completion queues for every CPU in the system, and up to 1,000 vectors so that we can get interrupt vectors for every CPU as well. And relative to the ASIC generations, the first chip that we put out supported a little over 1 million IOPs. The second chip that was put out several years ago is about a 1.5 to 2 million IOP range, about 2x the previous chip, or excuse me, 50% higher than previous chip, and we had latencies in the 25 to 30 mic level. And the recent ASIC that we've started shipping, our 64 gig product, has this architecture that supports 5 million plus IOPs with latencies sub 10 mics. And that's really the driving force for making the LPFC modifications. But of course, the trick with LPFC is we still have to support the older generation, and it's all got to work coherently. Now, we knew instinctively that the LPFC driver had done things for the old architecture and really hadn't supported the new architecture very well. So we needed to benchmark where it was to figure out where our starting point was. Now, when you look at this, you'll see 2 data points that I typically benchmark. One is a single port number, which is what we get on a single function with all the chip resources trying to drive to the one function, and then a 2-port number, which is a 2-port HBA, which is an aggregate performance level that we can drive over the 2 PCI functions. But in general, when we're doing the optimization, we're targeting in single port and trying to take it as high as we can. So we benchmarked both SCSI and NVMe. They're both supported by the driver. The interesting thing is when we look at our Gen 6, which is the 2nd generation older chip, we came in under 1 million IOPs, which isn't the chip's maximum on a single port. But yet when we look at the 2-port, we hit about the chip's maximum. So at least the bottom line, which is the blue dash line, we see we're being held up by something. And when we look at the Gen 7 product, which is the orange lines, we see the single port come in at about 1.5 million, which is way under the 5 million that we know we can support. And the 2-port still a little over 2 million, so we're off by a lot. So we've got a lot of headaches going on there. And then when we look at NVMe, which we know has been written to be a lot leaner and meaner and can drive us harder, the good news is when we look at our Gen 6 product, we find the 1-port and the 2-port being right on top of each other at roughly the adapter numbers. and that's what we would expect to see. But on the Gen 7, we find that the single port's under 2 million, the two port's still only around 3.5 million. So obviously there's a software deadlock or bottleneck going on there. So let's try and find out where the bottlenecks are. Are they in the stack or are they in the driver? So the first thing we do is we hack up the driver, create a switch so that when we flip the switch, all the I/O that comes down is immediately flipped back around to I/O completions and simulating an I/O interrupt. So we eliminate all the driver code paths, all the hardware interaction paths, and we can try and figure out how many I/Os per second and how well it scales as we add more CPUs across CPU sockets. So the simple graph to view is the one on the right for NVMe. And amazingly, it has one of those nice 45-degree bars that you almost never see. And it scales all the way up as far as you can take it to 96 CPUs. And as we go across CPU sockets, we find that it doesn't drop very much. So let's hold it, Christoph. So these are, the benchmarks on this were run in kernels that are roughly somewhere between 416, 419. This is SCSI MQ. Okay, so on this, we obviously have a different story on the left-hand side for SCSI. And the first thing we see is when we look at the first socket, we have the linear increase like we did with NVMe. But as soon as we hit that socket boundary, we see that it drops, it raises a little more, but as soon as we cross another socket, it drops more. And at that point, we start going downhill. So there's obviously things in the SCSI side that need to be looked at, and we'll keep that in mind to work with the community as we go further. But from our perspective, what we really wanted to see was, what do we expect out of the stack for scaling? How will that impact our driver? And what kind of numbers would we expect? And certainly our 5 million is certainly within bounds here, except for the SCSI side. So we took a look at the driver. First thing is code reviews and so on, and there were some obvious low-hanging fruit that we took care of. Things like a completion lock that was port-wide, done in every completion, which as soon as we removed, bumped the performance by 15%. There's other things like doing atomics for some of the statistics counting, trying to make them finer granularity, typical techniques. But there were 3 major areas that we had to do some serious work on the driver. And I'll go through those now. So the first, and this is not a new concept or anything else here, we just wanted to do CPU affinity on everything that we're doing. Take the I/O in, do the I/O completion, take the interrupt on every CPU, keep it localized to the CPU if at all possible. So this is just common, straightforward things. So what we do is we take with the SLI4 architecture, we have a work queue for commands completion, a command queue for the responses for that work that's submitted on the work queue, and we create one of those pairs, or a hardware queue in our terms, for each CPU. Now the completion queue is related to our event queue in the hardware, where whenever a work item is put on the completion queue, it can post a basic summary event to the event queue that says there was work on CQX. And it's tied into our interrupt handling processing to know what thing needs to be serviced as part of the interrupt handling. Now the EQ itself is one-to-one to the interrupt vector. So when there's work added to an EQ, it looks at its ARM state and then decides whether to drive a hardware interrupt or not on that. Now, the goal, as I said, was on a per CPU basis, have both the interrupt, the completion queue, and the work queue per CPU. But we know there are certainly circumstances where we can't get all those resources. Systems won't give us all the interrupt vectors we need. They'll be limited to some subset of CPUs, or when we go to create queues, perhaps there's far more CPUs on the system than we actually have hardware resources in the chip at that point to create the one-to-one mapping. So there's a balancing algorithm. It's very similar to what Christoph put in the IRQ logic that basically balances the resource to the sockets and then within CPUs within the socket. The thinking being, if we have a CPU that doesn't have one of these one-to-one resources, it'll share it with its buddy CPUs, and because the contention on that is within the socket, we end up getting better performance. Now, even though we have a lot of things that can be per CPU, there obviously are some adapter resources that can't be per CPU. And one of those that we have is what we call an exchange resource. It's used on every single I/O. It's used by SCSI or NVMe. And we have to figure out how to move those around. When we do an equitable distribution against some of these systems, even though we have 10,000-ish resources, by the time you divide that by 100 to 200 CPUs, which much of the system has today, it becomes only a queue of 10-ish, 20-ish, 30-ish. It's a very small amount. And you blow through that like nothing on a per CPU basis. So what we did is we added a mechanism where we have a local private queue, which is kind of the fast path for the CPU. And then each CPU also has a shared area. And think of that as kind of an overflow area. And the overflow area is the point where we designed where the contention between CPUs will end up being. So when we first come up, we do an equitable distribution. We put them in the shared areas to begin with. And as the CPU starts issuing IOs, it goes to pull from its local queue. And the general gist is it'll pull the resource off the local queue. It'll submit it to the adapter. It'll attempt to replenish that resource off the shared resources. And then when the I/O completes, the resource will go back on the local queue, and as we pass watermarks, it may push it back on the overflow list. Now, in the cases where we need to replenish the local queue, when we go to the local overflow, it's very possible that the local overflow may be low or non-existent or empty. So in that case, we need to go to a different CPU to steal resources. So what we have that algorithm do is on a one-by-one basis, it goes to a particular CPU, goes into its shared or overflow queue, and tries to steal resources from it and over into its own queue. Now, the intent is that we only have a couple of CPUs contending on a shared queue at one time. So we have every CPU working independently. They'll pick different CPUs to try and steal from at each time. And obviously, I/O load helps randomize this a little bit. Plus, we also optimize them by keeping them within socket first before going cross-socket. Therefore, when they do contend, it's actually a lesser penalty. And this has actually worked out pretty well, and because of the resource count levels, we've typically found there's a lot of sharing within socket, but not as much that's going cross-socket. And this has allowed us to keep the performance levels up while sharing this relatively critical resource. Now, the third area that we had to do some modification in is the interrupt handling. And the first thing we did that's paired to when we did the affinitizing and the balancing aspect where we know we don't have enough interrupts for every completion queue or every CPU. So we divided our ISR handler between the EQ and the CQ. In the past, the ISR handler, the hard ISR handler, came in, serviced the event queue, serviced the completion queue, and then exited. But because it's the hard interrupt handler, there's only so much time that we should be in that. And the amount of times that we're going in and out of that handler was extremely high. But by moving it down to the event queue and by separating the CQs into the per CPU part, the hard IRQ handler can become an entity that just says, I have work for CPU X, fire off a thread for CPU X. And CPU X, its deferred interrupt thread comes in and says, okay, I'm going to process my completion queue, and I will stay on that completion queue for X amount of time, as long as there's work to service. Now, we scheduled the length of time that we can be in that deferred thread to rather high levels. We measured what a basic completion context back into the I/O stack was and came up with numbers that equated to about a millisecond to a millisecond and a half, which we deemed was the maximum amount of time we'd sit here and spin in this loop processing work. If we ran out of work, we would simply terminate, rearm the completion queue, which would rearm the events into the EQ, which would then rearm interrupts. But if we had additional work, we would give up the CPU so the rest of the system could do something useful, and then we'd schedule ourselves for immediate reprocessing. And then this way, we ended up getting most of the advantages of a pulled logic while still falling back to immediate interrupts in the cases that we needed to. And it also said that out of the box, if we are under a high I/O load, thus there's always work coming through the completion queues, we spent most of our time in the completion handlers, processing those CQs. But if we were running latency loads, which were really just one work element in the completion queue, we allowed the immediate interrupt enablement from the EQ to CQ, which gave us our default latency numbers also staying up. So we were reacting to whatever the load was without dynamically tuning for the benchmark. This worked really well until we got onto a kernel system that had the APIs for the IRQs to set affinities, but didn't actually implement the internals of them. And so what they ended up doing is sticking our interrupt handlers for 100 CPUs all on CPU 0. So we had CPU 0 just sitting here spinning in hard ISR handlers for 150 vectors. And needless to say, we soft locked up. So we still had to put some of the normal interrupt delay logic in there just to stop that type of behavior. So we watched how many interrupts off of how many vectors were being done on the particular CPU, slowed them down so the CPU could actually get a little work, and then we actually went back to the systems and tried to get this behavior resolved. The end results that we got is we moved the SCSI single port numbers from 1.5 to 3.75 million. And the two port numbers from 2 million to 4.5 million. We moved the NVMe from sub 2 million to 5.2, and the two port at 5.3. Now, they're actually, the 5.2 versus 5.3 is starting to look like our hardware limits are kicking in at the aggregate level there. And we've actually gone back and tuned some of the hardware, and we're now seeing actually about 7 million aggregate off of this hardware. But you know, we overall look at a 2x and a 2.5x improvement as, you know, we're keeping up with the hardware now. And as good as that is, we've also done a bunch of latency benchmarks, single IO at a time. We're consistently seeing a latency of about 10.5 mics as measured by FIO, which is out at the application space. So the IO is going into the kernel, through the driver, on the wire, to the target, data and response coming back into the driver, completion, all the way back out to the application in the 10.5 mic. We've looked at the data paths where we pass through our hardware on either end. We believe we're about a mic to a mic and a half on each of those crossings, so we're about 6 to 7-ish of that 10.5 mics. So we're actually doing pretty good. And this is, the good news is all of this is out of the box with default settings. We're no longer tuning anything for interrupt delays, you know, how many I/O channels and all this other stuff. But there were a few interesting experiences that we had along the way. Now, this is a little bit of an eye chart, and I won't ask you to read the numbers, but pay more attention to the colors. And what this is 3 different systems that are of slightly different ages in kernel, which means they have slightly different sets of kernel patches merged. And we saw a rather interesting result that when we increased some of the I/O counts per logical unit that we had in the configuration, when we crossed the queue depth, the IOPs would drop. The floor would go out from underneath of us. So on the oldest system, we saw we could be hitting 4 million IOPs, and as soon as we got above the SCSI queue depth values that were configured, it dropped to 100,000 IOPs, a 1/10 of performance. When we looked at it, what it ended up being, it looked like the I/O retry logic got into a busy loop that wasn't stalling, and therefore got into a very tight loop, sucked up all the CPU, made the interrupt processing threads on the CPU have a very difficult time to run, and it basically caused all kinds of headaches. Now, the concerning part is this was done on SCSI, so it doesn't take very many IOs per logical unit to exceed its queue depth. So it doesn't take long for you to hit this issue. On NVMe, the same kind of thing exists, but because the depths are now at a controller wide rather than namespace wide, it's actually a little harder to get into this scenario, but it still exists. Now, as we went into newer kernels, the other interesting thing we found was When you're on the newest kernel, it actually didn't drop off that much. And the middle one got better. And that's kind of the red versus purple versus everything's all green. So obviously, upstream guys have been fixing this as it's been going along, but there's some history here that we need to help work out with the community and the distro folks to make sure that this all works right and that we don't have regressions. But the other thing that we also saw in this is the newer OS actually dropped in overall performance, which is another thing that we've got to go and take a look at. You know, we went from 4 million down to 2.5 million, and although that 2.5 million never really dropped as we got above these other limits, the fact that it went down is something that we've got to go and take a look at. And it is the same driver source on all these systems, so there's other things that are contributing here. So, needless to say, we're not done in this story. We have a couple of areas that we definitely want to keep attention on, such as the SCSI MQ behavior and cross-socket scaling, and the issue that we saw in retry policies, and so on in the last slide. We also have a few things in the driver where there are still locality and data structure breakouts that we want to do. But there's a few other things that we want to take a look at, like considering when you are out of CPU on a single CPU, does it make sense to start borrowing cycles from idle CPUs for some of the I/O process? Or is there cases like I/O resource sharing where maybe we're better off using the request queue to simulate the same kind of algorithm that we put in for our shared algorithm? And that's it. Yep.
Questions for Dave?
Good.
So I have a question.
Sure.
In the middle, you had a performance chart at the provider. You had a chart that you were showing more than 4 million. And then you were in the small 10 slide back. And then you went as low as 2.5 million. So what's your sense of where's the hardware device?
The hardware device, we have done hardware simulation and verified it can do well over 5, even 7+-ish. And the graphs that we're now getting in the benchmarks, we are consistently through the software paths getting 4 to 5 to mid-5s. And now with the hardware tuning, we're getting the 7 million on the 2-port aggregate. So we're seeing a single adapter, 2 ports, averaging 3.5 million each. Okay, but if you can drive with single port, and you can be taking that entire 7 million and focusing it on the single port. Yep.
We got into that. So these IOPs are 1K IOPs?
These are 512 byte. And it won't change too much in these graphs because we're not quite at the bandwidth limitation on the link. We actually have room at some of these, but when you saw the first graphs when we measured the driver, you could see where we started hitting the downward trends where we were actually being constrained by bandwidth on the link. But we certainly have room up until about the 2K range where we're not constrained by the link.
Anybody else? Definitely impressive.
Good, thanks.